Okay, today's day 3 of our getting ready for quantum physics. The big foundational idea that we learned in our last lesson is that the difference in path length determines the type of interference that we get. So if both beams of light start at the same spot and travel the same distance, we have a difference in distance of 0, and that's constructive interference. If one beam of light travels an extra half a wavelength, we will get destructive interference. And if one beam travels an extra wavelength, we will be back to constructive interference. This pattern will continue indefinitely. Integer wavelengths give you constructive, and integer plus a half gives you destructive. Remember, delta x is the difference in path length. So we had interferometers where we could have one beam possibly travel farther than the other. That could lead to constructive or destructive interference. Today we'd like to introduce you to a new term, something that's super important in science. It's a phenomenon known as diffraction. Diffraction refers to the spreading out of waves after passing through a narrow opening. So let me explain. These red lines represent waves of light, or waves of water, or waves of sound. They're going to pass through a narrow opening in a barrier, and when they emerge on the other side, you can see how the waves spread out as if they are a brand new source of sound or light or water waves. So diffraction again is the spreading out of the wave after passing through a narrow opening. We can actually see this phenomenon in our waves in Google Maps. Okay, if we find just the right geometry along the shoreline where we have some wave breaks with a small opening in them. When the waves pass through this opening, you could see how they spread back out as if they are a new disturbance, creating a new wave from that spot where they pass through the barrier. Notice with this one, the barrier is a little bit too wide. So although we get this curving arc on both sides, I think you can see in the middle how it's no longer following that circular pattern. So in order for diffraction to be a true source of wave, that is forming the characteristic circular arc or spherical arc in 3 dimensions, the opening has to be properly sized to the wavelength of the wave. Okay, so let me show you. With a light wave, we can make diffraction. So we take 2 wood splints, we're going to hold them up in front of the laser, and we're going to move the 2 splints closer and closer together, making a smaller and smaller opening. What I'd like you to watch is the pattern that emerges on the wall. So as the light passes through a smaller and smaller opening, you'll see the light starting to spread out. When I get the opening of the right size, you can see how the light spread out in both directions. Notice how I'm holding the sticks vertical and the spreading out is happening horizontally. If the sticks were horizontal, it would have spread out vertically. Okay, so the important idea is that waves will diffract. That includes light waves, sound waves, water waves, and in order for diffraction to happen, the opening must be properly sized. Here is a barrier that has a bunch of different slits carved in it, so we can get multiple sources of diffraction. Now this one happens to have the openings that are a little bit too large for us to use for light, but they're very visual, so you can see what this phenomenon would look like. Okay, so again, multiple openings, multiple slits. Each one, when the wave passes through, will act like a new source of waves. So, for instance, down the shore here we have a wave break that has 2 openings in it. And I hope you can see how there are waves that appear to have originated in both of these openings. So we got some curves that way and some curves this way. both of these are acting like a new source of waves. Here's the key thing. These waves are now overlapping, and overlapping waves will interfere with each other. And that's why diffraction becomes such an important idea, is that we can take a single wave, turn it into multiple waves, and have those waves interfere with each other. So with our waves drawn out like this, again, we have one wave to start with, passing through two different openings, and that is going to create what appears to be two new waves. The important thing is both of these waves will have the exact same frequency because they came from the same source. They will be perfectly synchronized because they came from the same source. They will have the same amplitude because, again, they came from the same source. Okay, so these waves are going to be identical, but we turned one wave into multiple waves, and these waves are now overlapping. If you look, where are they overlapping? Well, there's some patterns. You can see if I go to the midpoint between these two openings, there will be a line of dots where these things are overlapping. It turns out anywhere along that line will be constructive interference. Okay, constructive interference. The wave fronts are overlapping with other wave fronts. Okay, turns out that they're not the only place we get constructive interference. We can see another pattern, both above and below, that forms again another line that when it hits this wall will form a bright spot. So this gray thing is a wall that we put in the path of this light that has passed through the diffraction grating. And we see, right in the middle, we get constructive interference, we get constructive interference, constructive interference, and right in between, destructive. Okay, where we don't have wave fronts meeting wave fronts. We would have wave fronts meeting non-wave fronts, which would interfere destructively. You can see it's not just here, but we get another set, and another set, and another set. So here, we see our pattern symmetrically placed around the center of areas of constructive interference. Let me show this to you in real life. So we have a diffraction grating, not like the one I showed you before where you could see the slits and there were 5 of them. Here we have 300 openings per millimeter, so these are incredibly small. You cannot see them with your normal eyes. We're going to shine the light through that diffraction grating, these multiple openings. It's going to create a whole bunch of waves that are going to overlap and form the pattern that we are expecting of bright spot, dark spot, bright spot, dark spot, bright spot. So let's see it. Okay, so if you look right here, you'll see the laser before it goes through the diffraction grating. And then when I put it through the diffraction grating, I hope you can see bright spot, bright spot, bright spot, bright spot. And on the other side, the same exact pattern. In between the bright spots, we have dark spots where we have destructive interference. Okay, so to summarize, we start with one light. We send it through a grating that has these little openings that are going to produce new sources of light. These new sources of light overlap. They might overlap constructively and they might overlap destructively. This will form a characteristic diffraction pattern on the wall of bright spots and dark spots. There are 4 variables you should know when studying this: the wavelength of the light, the distance between the openings in my diffraction grating, the distance between the grating and the wall, that goes by L, and then how far it is from the central dot to the first dot, or to the second dot, or third or fourth. All right? That's called your delta Y. We would like to do a little study to find out how these 4 things are related. So in lab, that's what we're going to be looking at. Before we do, I just want to make sure it's crystal clear why we're getting these bright and dark spots. So here is a straight line from the top hole and the bottom hole. I'm going to label it A and B. The light that came from A and the light that came from B traveled the exact same distance to get there. So the difference in distance traveled by those waves is 0, so they are going to be constructive interference. When we look at the dot that is above the central dot, I hope you could see that this bottom wave had to travel farther than the top wave. How much farther? Half of a wavelength. I'm sorry, 1 full wavelength. Because this is a bright spot, the difference in path length must be 1 wavelength. When we get to this one, it's going to be 2 wavelengths. Okay? This one has now traveled a lot farther than that one. How much farther? 2 wavelengths. Okay, so by understanding how all of these variables fit together, which we will do in lab, so you don't know how to do this yet, but by knowing how they fit together, we can study a lot of things, especially in astronomy and also in chemistry, to figure out this guy, the wavelength of the light that we are looking at. That will be important to tell us what stars are made out of, or maybe what chemicals we're looking at as they glow and give off light. So diffraction grading is very important for astronomy, for element identification, and the idea that we're seeing in diffraction will become very important with quantum physics, as you will see. So I'm going to pause it here, lab tomorrow, and best of luck.